just want to show you guys how to go about these things. I saw a lot of persons making a lot of mistakes, okay, and not getting to follow the procedure correctly. Okay, now in this experiment, you expected to standardize the permanganate using the iron sulfate. Okay, after standardizing it, you titrate it against the oxalic acid to determine the molar mass of the oxalic acid. So now, what this means that standardizing the potassium permanganate with the iron would help you to find the exact molarity of solution B, which is the permanganate, meaning that your second table is where your calculation is going to start. And in that case, if you check your redox reaction, you get to see that 5 moles of iron 2 required 1 mole of the permanganate. All right, okay. So there is something I want you guys to understand and how to do these calculations much easier. This is mole, this is mole, right? So there is this formula that says number of moles is volume times concentration. All right, now bearing that in mind, I'm going to equate the volume times concentration for the iron, volume times concentration for the permanganate. All right, since this is number of moles, this is number of moles. So what is the volume times concentration, which is the number of moles of iron in this case? The volume times concentration, the volume of pipettes you had taken for the ammonium sulfate. What was the volume you took? 25, right? So divide that by 1000, because we are working in dm cube, times the concentration of the iron from your manual is 0.1. This is volume times concentration, which is still number of moles. Now let's do the same thing for the permanganate. All right, what was the volume of the average volume of permanganate in your second table of values? All right, so that's going to be, let me use as an example, let's say this were to be 26.5. Let's say that's what you got as average permanganate for the second table. All right, so divide by 1000, multiply by what is the concentration? We don't know it. This is volume times unknown concentration. This is volume times known concentration, and this is the mole because number of moles is volume times concentration. Now in this case, I'm going to wipe 25 multiplied by this, divide by 1000. I'm going to wipe this off, so that will give me 0.0025. Can you see that? So when I divide 26.5 by 1000, then multiply by x, that should give me 0.0265x. All right, so the next thing you're going to do, remember there is a 5 here. The next thing you're going to do is just multiply this by this, equate it to multiplying this by this. So I'm going to have 5 multiplied by 0.0265 with an x. 1 times this is still that 0.0025. Okay, now for me to find my unknown concentration, whatever this gives me, okay, if you should multiply this correctly, you should be having around 0.1325x. okay, let's just break that down. All right, so here we divide both sides by 0.1325, 0.1325. okay, now if you do this correctly, okay, we're going to have, so when you divide this, you should be having around 0.0189 molar. That is for the concentration of the permanganate. Can you see this value? This value that we've gotten, let's analyze it so that you understand what I mean. So our concentration of the potassium permanganate now in this case is 0.0189 molar. Now this is the exact molarity of solution B. This is the exact. Remember, if you go through your procedure, you were told that you were given an approximate 0.02 molar permanganate. Can you see how exact this value is? Because if you take the approximate value of this, you get back what you were given. So this is the exact value, but this was the approximate value you were given. So anything falling short of a value like this, or let's say you had 0.1, this is not correct. Okay, or let's say you had 0.02, exactly 0.02, this is not correct. Okay, your value should be the very much exact value for the concentration of the permanganate, such that once you approximate your answer, you should have what you have in your manual. All right, so this is the exact concentration of the permanganate. So that is how you go about doing that. If, for example, maybe your volume of permanganate in this case was 26.5, like I've just said. So in the next one, you are asked to find the molar concentration, right? Molar concentration of solution A. We can still use the same method that I've just showed you again. Now, molar concentration of solution A is that of the oxalic acid. So you go back to the first table, all right? Because the first table had to do with the reaction between permanganate and the oxalic acid, right? Let me write it. If you check that redox titration, you get to see that 2 moles of the permanganate required 5 moles of the oxalic acid, right? Remember, we want to find now the molar concentration of solution A, molar concentration. What we just did now, we are repeating it again. So this is number of moles, volume times concentration of the permanganate, all right? Volume times concentration of the oxalic acid. Remember, we've gotten to know what the concentration of the exact concentration of solution B is. So what was the volume here? In that table, in the first table, what was the average volume of permanganate that was used? Remember, we've said, let's take for example, let me also take for example that your volume was 26.5, which I don't think it should be. Anyway, this is an example. Let's say the average volume in the first table was 26.5. So divide by 1000 again, multiply by, what was the concentration you got? Remember, we've just calculated the concentration to be 0.0189, okay? Don't approximate. What was the volume of oxalic acid you pipetted? You pipetted 25. So that's going to be 25 divided by 1000, all right? Multiply by the concentration that we don't know. This is volume times concentration, which is mole, volume times unknown concentration, which is mole. Can you see that? Just what we've just done in the previous. So if you multiply this by this, divided by 1000, 0.12350, okay? Then if you should do this, multiply by x, of course, you just have the same thing, 0.025x. Can you see that? I believe you know the next step to take, all right? So all I'm going to do is multiply this by this, multiply this by this. So I have 2 multiplied by 0.025x will be equal to 5 multiplied by that. That's 0.12350 times 5. Can you see that? So if you do this multiplication, you will have 0.05x will be equal to, if you do this, you should be having around 0.12251. Okay, so divide both sides by 0.05, 0.05, so you should be having around 0.050 molar. So can you see that? So this is the concentration of the molar concentration of the oxalic acid. You see how straightforward it is, right? So this is how you go about doing these calculations. And then if you want to determine the what is it called, the molar mass of the oxalic acid, which is supposed to be the aim of this experiment, just don't forget the value we just got, that is 0.05. all right? So we need a relationship. You know, this is now the oxalic acid, right? C2O42 minus, okay? The oxalate ion. We want to determine the molar mass of the oxalic acid. Now, remember, we have a relationship that says molar concentration equals to mass concentration divided by molar mass. This is what we're interested in. Mass concentration, we can get it, right? Molar concentration, we just solved it. We just got this to be 0.05 for the oxalic acid. The mass concentration, we can get it. What is the mass concentration gram per dm cube. You were served 1.6 gram from your procedure in 250, right? So we are working in dm cube, so how much will be in 1000? All right, if you multiply this by this, we want to get the mass concentration in gram per dm cube, right? That's why we are multiplying, and we are making use of 1000 now. All right, so 1000 multiplied by 1.6, all right, this multiplied by that, so it's going to be 1000 multiplied by 1.6 divided by 250, and that should give you 6.4. And this is now going to serve as your mass concentration in gram per dm cube for the oxalic acid. While we know the molar concentration, we can now get the molar mass. Now, how do you do that? This is 6.4 and this is 0.05. So let me write this again. So that means I'm going to have equals to 6.4 divided by molar mass, this over 1. We can do the same cross multiply, this multiplied by that, 0.05 molar mass, right? Please let's make it molecular weight. Let's just use this so that someone doesn't think it's millimeter. All right, so this times this is 6.4. so now I divide both side by 0.05, divide by side by 0.05. so this can cancel, right? So when you do this correctly, you should be having around 128. Yeah, 128. So the unit is gram per mole. Now bear in mind, your units are very important. Don't just write a value, or don't write 128 gram and you exclude per mole. You'll be wrong. So the unit is gram per mole. So this is the molecular weight of the oxalic acid. The molar concentration you just calculated, converting the 1.6 gram to was served in 250 to 1000, you got water of crystallization coming from the oxalic acid. This is oxalic acid, H2C2O4. All right, this is oxalic acid, but that's water. All right, so you're going to equate the 128 gram per mole you just got. That's the total weight. Okay, this is what you do. Please don't confuse yourself with this. This is just OH 2x water. This is C2. This is 2 times 2. That is, look at it here. The oxygen is now 4. Then we have, where is it? Hydrogen, H2. Okay, that's what happened here. It's still the same thing. Okay, so when we do this correctly, so this is 2 times 1 hydrogen plus 16, 18. So I'm going to be having 18x here, which will be equal to 128. All right, so I'm going to have 18x equals to 128 minus 90. All right, so 18x will be equals to 38. Divide both side by 18, divide both side by 18. So you should be having around 2.1, okay, which is approximately 2. That means the water of crystallization is 2. So that means your x is 2. So this is essentially how you go about doing these calculations and doing them rightly, so that you don't get to copy and all of that and you just mess up the whole thing in your exams. So this calculation now is just serving as only one revision out of the 5 experiments that you've done. Okay, this is how you go about these calculations, and good luck.